Okay, here I will try to solve a least square problem using the QR factorization. Okay, so a least square problem basically is when you have you have some set of data and nothing in this set of data really matches the two values. Okay, so let's say you have your matrix A and you have your set of data in the vector X, and your real values, so your ideal values basically are in the vector C. Basically, if you subtract your ideal values from the values you collected contained in the vector X, you should get 0. But in a least square problem, this isn't the case. You will get some vector R which contains the error margin. Basically, it will maybe be a small value, but you won't get exactly 0. And the goal will be to find the most accurate set of data, the one that matches is the best accurate. Okay. And we can use the QR factorization to do that. Okay? So recall that the QR factorization is when you decompose a matrix A into two matrices Q and R, where Q is orthogonal and R an upper triangular matrix. Okay? And so recall that R can be found if you multiply A by Q transpose. Okay, and then we will solve the least square problem in the following way. We will find a vector D, which is defined by Q transpose C. So C is the ideal set of data. So the set of data you get at the beginning, okay, and then you will find your set of data in the vector X with the following: R0 X equals D0. Why R0? Because what can happen is that in your matrix R you have some values, and then you have some rows that contain only the element 0, so they contain basically nothing, and you won't use that rows because basically they don't help us to find the closest data possible. So R0 will be the matrix where every row has at least one non-zero element. Okay, and D0 basically is defined in a similar way. When you cut some rows in R, you will also cut them in the vector D. Okay, so let's say your matrix R and D have 4 rows at the beginning, and in your matrix R you cut 2 rows. So you have your vector D, which doesn't it doesn't have to have 0 components in its rows too. Okay, here we will cut. So you will cut basically the last 2 rows. Okay, so you will only get two non-zero rows. Okay, so it's defined that way. Okay, so our goal is to have a matrix R that has only rows that contain at least one non-zero element. And so you can solve for X once you have found D, which is given by Q transpose C. Okay. So I will do an example. let's say we want to solve the following problem. Okay. So, sorry. So this is our matrix A. This is our real. So this is the set of data we want to determine to get the closest, the best result, basically. And these are our the values we got at the beginning, contained in the vector C. And so I will find the QR decomposition of A, this matrix here. For that I will use I think I will use a givens rotation. Okay. So let's redraw our matrix. We want to eliminate this element here. Okay. So it's the Z element because we are in 3 dimensions. So we can rotate around the X axis, or we can also rotate around the y-axis. Okay. So first, let's determine our cosine and sine. So our cosine will be the element at the top of the vector. So 1 over the square root of 1 squared plus the element we want to eliminate, so 1 squared. And our sine will be given by the element we want to eliminate, so 1 over square root of 1 squared plus the element at the top of the vector. So that will give 1 over square root of 2, 1 over, square root of 2. Okay? And so now we have our first matrix G1. Remember that the formula, the minus sign, is always in the same place as the element we want to eliminate. Okay, and here we will rotate around the y-axis. Okay. Sorry. So this will be 1 over square root of 2, negative 1 over square root of 2, 0, 0, 0, 1 over square root of 2, 1 over square root of 2. Okay. And now if we apply it to the matrix A, we'll get a 1, which will give us, if you do the computation, the following. Okay. Yeah. Now we want to eliminate this element here. Okay. So our cosine will be given by, remember you have to consider the submatrix, okay, in order to avoid problems. So it will be 1 over the square root of 1 squared plus 1 over square root of 2 squared. This will give us it will be 1 plus the square root of 3/2. So the 2 comes on the top, so get square root of 2, square root of 3. Okay? And for the sine, you will get, it will be 1 over square root of 2 over square root of 1 over square root of 2 plus 1 squared, which will give us 1 over square root of 3. Okay? And so our second matrix will be given by, we have to place the minus sign in the place of 1 over square root of 2. Okay, so it will be given by, just, we will rotate around the x-axis. It will be negative 1 over square root of 3. Think this is correct, should be. So if you apply it to your matrix A1, there's a problem here. Why just, no, everything is okay. I was troubled with something, but it's okay. You should get, to do the computation, you should get square root of 2. So the first column doesn't change. It shouldn't, otherwise there's a problem. And then you get 0. Okay. And so this is our upper triangle matrix R. Okay. And now, so R0 will be, let's do it, R0 will be, remember we only consider the rows where there is at least one non-zero element, so it will be square root of 2, 0, 1 over square root of 2, square root of 3 over 2. Okay? Now let's find our vector D, which will be first we will find our matrix Q. So remember that Q transpose A equals R, but we found R using J1 and J2. So J2, J1 transpose is equal to Q, so J1 transpose, J2 transpose is equal to Q. Okay? But I think we don't really need to do the transpose because our D will be defined by Q transpose C. Okay. So this is J2 and J1 basically. and the vector C. And so we can already find D0, so we will only consider the two first rows of D, because we only consider the two first rows of R. So if you do the computation and then only consider the two first rows, you should get the following. Okay, so that will be the 0. Okay, so you can do the computation. And then now we will find the vector x. We will use R0 x equals D0. So this will give you the system of equation. You can row reduce, and then you should get the. So let's maybe draw it a bit. You will get. So let's just write it again. Times x is equal to okay, so you can put that in matrix form. So square root of 2 1 over square root of 2 okay, you can row reduce, and then you should get that x2 is equal to 61 times square root of 3 times square root of 2 over square root of 2 over square root of 3, so 61. And then you should get that x1 is 1 over square root of 2 times the following. So 121 over square root of 2 minus 61 over square root of 2, which will give you, so that will give you 60 over 2, so 30. And so these are your two possible values. So x1 30 and x2 61. So if you plug in that values, remember if you plug in that in ax minus c equals r, you should get the most accurate value, okay? The most accurate result. Because remember, there is no true values, no ideal values. This is a least square problem. We want to find the most accurate values, okay? So yeah, you can do using QR factorization. So just remember, once you found your QR decomposition, I think you don't even need to find Q, you just need Q transpose. So your matrix R is given by Q transpose A. Your vector D is given by Q transpose C. C is the set of data you have at the beginning, and R0 X equals D0 allows you to find X. So, and remember that R0 only contains rows with at least one non-zero element, and D0 will have the same numbers of rows as R0, even if D0 has some non-zero values in some rows that will be cut. Okay, you remove the rows according to R. Okay, so yeah, that's it. Thanks for watching.